So far, when we've talked about convergence, we've only considered sequences of random variables that take on single numeric values, as opposed to sequences of, say, random vectors, or multivariate random variables. In this discussion, we're now going to continue thinking about convergence. However, we're going to extend some of those notions to engage with convergence of multivariate random variables, and in particular, convergence in probability of multivariate random variables. We will see that this is quite important when we're thinking about combining different simple estimators to form a more complex estimator. As a motivating example, imagine we have n IID observations drawn from a distribution f still on the real numbers, and we want to estimate the coefficient of variation, in this case the standard deviation of a single draw from f divided by the expectation of a single draw from f. This parameter can be thought of as a standardized measure of variability. In this case, we are assuming that both the mean and the standard deviation are strictly greater than 0. One simple estimator we might consider using is this plug-in estimator, where we take the sample standard deviation and the sample mean, and we just look at the ratio of those two. While this is a natural estimator, it's unclear asymptotically how it behaves. One might ask, does this converge in probability to our original parameter? If so, what's the rate of convergence? And if we sufficiently zoom in on the sampling distribution, what does the shape of that sampling distribution asymptotically become? We note here that this estimator combines two simpler estimators in a not particularly complex way as a ratio. To engage with the asymptotics of this estimator, the first thing we're going to do is think about asymptotically what happens to the components of this estimator, the sample standard deviation and the sample mean, as a vector as the number of observations get large. In particular, can we think of this vector theta hat converging to this vector of parameters theta, and what notion of convergence would we have to use here? We're going to think about extending convergence in probability and in distribution in this multivariate setting. In this video, we're going to focus on convergence in probability. We're now going to give a formal definition of multivariate convergence in probability. This definition is going to parallel the definition that we had before when we were thinking about random scalars rather than random vectors. So here, we say that a sequence of random vectors, theta hat n, converges in probability to a fixed vector theta, and we write theta hat n converges in probability to theta, like before, if for any tolerance epsilon, we have that the probability of the distance between theta hat n and theta being greater than epsilon converges to 0 as n gets large. In this case, I'm using the infinity norm, which is the maximum of the absolute value of the elements in this vector of differences. One could actually use any norm in this definition, and they're all equivalent. This parallels what we had before in the scalar case, except instead of a norm here, we had an absolute value. However, when we're thinking about multivariate problems or random vectors, in fact, we need to work with a norm. The absolute value of a vector is not a defined quantity. Intuitively, this is just saying that the sampling distribution of this random vector fully concentrates around this fixed point theta. Going back to the problem we talked about before, thinking about estimating the coefficient of variation, here we note that the sample mean and the sample standard deviation converge in probability to the mean and standard deviation respectively. And I'm not going to show all of the details here, but it's relatively straightforward to show that if we consider these as a random vector now, that this random vector converges in probability to this fixed vector in the sense that we mentioned in the previous slide. This doesn't follow completely trivially from what we have right here, right? It's going to require a little bit of math because the definition on the previous slide is different than just saying each piece converges in probability. However, it's only a couple of lines to show. Now, how can we use this to tell us about the behavior of sigma hat over mu hat of our plug-in estimator? Might we use this to show that our plug-in estimator is consistent, converges in probability to sigma over mu? This is going to follow from a fairly slick theorem called the continuous mapping theorem. What this theorem says is, if we have a random sequence of vectors, Zn, and a fixed point z in p-dimensional space for p greater than or equal to 1, And if we have that this sequence of random vectors, Zn, converges in probability to Z, again in that multivariate sense of convergence, then if we select a function g that is continuous at that limiting fixed point z, if we look at g of Zn, that will converge in probability to g of Z. So basically, I've taken the continuous mapping theorem that we've seen before in one dimension, and now I have extended it to look at multiple dimensions. Now we'll see that that can be used in a pretty straightforward fashion to show that our estimate of the coefficient of variation converges in probability to the true coefficient of variation. So applying this to our problem, we have that the vector of components converges in probability to this fixed parameter vector sigma mu. And if we think of this map G that takes in sigma and mu and maps it to sigma over mu, if mu is greater than 0, then this map is continuous. So by applying the continuous mapping theorem, again, we have this playing the role of Zn from before, this playing the role of Z from before, this playing the role of G from before, and that tells us that sigma hat over mu hat converges in probability to sigma over mu. So now we have that our proposed estimator is consistent. And we've discussed this now in one example, but it's a pretty general phenomena. If we have a parameter of interest that I will call psi, that's a general parameter, if it's a continuous function of simpler parameters, in this case it was a continuous function of that standard deviation and population mean, then what we can do, a recipe for estimating it, can involve getting consistent estimates of those simpler parameters. Again, in this case it was sigma and mu, and plugging those in via that continuous function, and that will give us a consistent estimate of that combination psi. This is often known as a plug-in estimator, and it's a very common and fruitful strategy for building estimators of somewhat more complex parameters. So, taking this a bit further, the continuous mapping theorem told us that psi hat, our plug-in estimate of the coefficient of variation, converged in probability to psi. However, it didn't give us a rate of convergence. So can we take this a little bit further and maybe get a rate of convergence? To do that, I'm going to give a refinement to that continuous mapping theorem. So the continuous mapping theorem basically said if we have a sequence of random vectors that converges in probability to a point, then if we apply a continuous function, we maintain that convergence. So for this so-called quantitative refinement, I'm now going to look at the rate of convergence. So here, if we imagine we still have a sequence of random vectors that converges to a fixed point, if the rate of convergence, here I'm using infinity norm, it could actually be any norm, is at least as fast as some sequence delta n for a sequence delta n that converges to 0, then if we take a differentiable function g and apply g to Zn and g to Z, then if we look at the distance between these two, it is still bounded in probability by delta n. So let's say that again. If our original sequence basically converged at a rate of at least delta n, then when we apply a differentiable function with one bounded derivative to both the random variable sequence and the limit, then we get that the difference between these two is also bounded by that sequence delta n. So that seems sort of technical, but what's the point here? Well, the point is that we showed before using linearity or asymptotic linearity that mu hat, the sample mean, converges to the population mean at a rate of 1 over root n, and sigma hat, the sample standard deviation, converges to the population standard deviation at a rate of 1 over root n. And so from this, it wouldn't be particularly hard, a line or two, to show that the same is true if we consider the estimators minus the fixed parameter values as a vector and look in this infinity norm, that this difference as a vector converges to 0 at a rate of 1 over root n. And this map that before we noted was continuous, in fact, is differentiable and has a bounded derivative for mu bounded away from 0. And so that means when we stick mu hat and sigma hat in here and compare that to sticking mu and sigma in here and look at the difference, this difference the rate of convergence is roughly the same as the rate of convergence of this difference, or at least is asymptotically no slower. So what does that tell us? Well, that tells us that our estimated coefficient of variation converges to the true coefficient of variation at a rate of at least n to the negative 1/2. Excellent. So now we have a rate of convergence. Not only do we know that it converges in probability to our parameter, but we now know something about the speed of convergence. Here we've bounded the speed of convergence. It turns out this is actually sharp. This is the rate at which it converges, and we'll see that next. So if we're thinking about this again more generally, if we have some parameter of interest psi, and it is a differentiable function of simpler parameters, which in this case, again, we had that g function ratio that is differentiable, and we had those simpler parameters, sigma and mu. Then we can take consistent estimates of those simpler parameters, sigma hat and mu hat, and we can plug those in to our differentiable function g to get a consistent estimate of that combination parameter psi. And in addition, if we want to know about the rate of convergence of that plug-in combined estimator is at least the worst rate of those component estimators. So if you look at how quickly sigma hat converges to sigma and mu hat converges to mu, and you look at the worst of those two rates, in this case they were both n to the negative 1/2, the convergence rate of psi hat will be at least as fast as that worst of the two. And generally it's actually precisely equal to the worst of the two.